So get this. What if I told you that two of the most common problems you'll see in coding interviews, and frankly, in a ton of real-world programming, can be solved beautifully with just one simple tool? Well, today we're going to master both of them. Think about it. You've done this a million times. You type an expression into a calculator and it just knows the order of operations. It doesn't just read left to right. How does it do that? This isn't just a random math question. It's a really fundamental puzzle in computer science. And believe it or not, that puzzle is deeply connected to this one, figuring out if a string of brackets, parentheses, and braces is perfectly matched up. So today, we're solving both. We'll start with a classic balanced brackets problem and then level up to evaluating some pretty tricky math expressions. So, what's the secret weapon? What's this one simple tool that can do all that? It's the stack. Okay, let's dive in and see exactly what makes it the perfect fit for these kinds of challenges. A stack is what's called an abstract data type, which sounds complicated, but all you have to remember is one simple idea: LIFO, last in, first out. Seriously, the best way to picture this is a stack of plates at a buffet. The last plate you add to the top is always the very first one you take off. That's it. And for everything we're doing today, we only need two basic actions. Push is just adding a new plate to the top of the stack, and pop is taking that top plate off. Push and pop. It's almost unbelievable, but with just these two simple moves, we can solve both of our puzzles. All right, let's put it to work. We'll start with our first puzzle and see just how perfectly that last in, first out idea solves the whole nested brackets problem. This one is a classic for a very good reason. Okay, so we're going to walk through this string one character at a time. The first rule is super simple. If we see an opening bracket of any kind, we just push it onto our stack. So first up is an opening parentheses. Boom, we push it on. Next up, we see an opening square bracket. Same rule applies. We push it right on top of the stack. So now that parenthesis is sitting right under the square bracket, just like our plates. And we do it one more time. We hit the opening curly brace, we push that on top too. Now take a look. Our stack is a perfect mirror of the nesting in our input string. It's holding the parentheses, then the square bracket, and the curly brace right on top. Okay, now here's where the magic happens. We've just hit our first closing bracket. So here's our second rule. When you see a closing bracket, you peek at what's on top of the stack. Does it match? Well, we have a closing curly brace, and hey, what's on top of our stack? An opening curly brace. It's a match, so we just pop it right off. We've successfully closed that pair. We just keep doing that. The next character is a closing square bracket, which matches the square bracket now on top of the stack. Pop. Then the closing parentheses matches the last item. Pop. And what are we left with? An empty stack. And that right there is the key. If the stack is totally empty when you get to the end of the string, it means everything was perfectly balanced. It's a success. If we had an invalid string, like on the right, we'd be left with something on the stack. And that's how we know it's a failure. All right, you've totally mastered brackets. Now let's really level up and use the exact same tool to solve that calculator problem, to make sure a computer evaluates a math formula in the right order. For this, we're going to use a really famous algorithm from the legendary Edsger Dijkstra. It's called the Shunting-Yard algorithm. Now, its whole job is to take an expression that's easy for us humans to read, called infix, and convert it into a format that's super simple for a computer to handle, called postfix. You might also hear it called reverse Polish notation. Postfix is awesome for computers because there are no parentheses and the order is completely clear. You just read from left to right. I think the absolute best way to visualize this is with a simple analogy. Just picture you have two things, an operator tray right beside you, that's our stack, where you can hold on to operators for a little bit, and then there's a conveyor belt moving in front of you. That's where our final output is going to go. Let's trace our expression, 3 plus 4 times 2. First token is the number 3. The rule for numbers is easy. They go straight onto the conveyor belt. Done. Next, we see a plus sign. Our operator tray, the stack, is empty, so we just put the plus on it. Then we see the number 4. Again, numbers always go straight to the output. Now it gets interesting. We hit the multiplication times symbol. We have to look at our operator tray. It has a plus on it. And here's the crucial rule. Is the new operator more important? Does it have higher precedence than what's on the stack? Yup, multiplication beats addition. So we can just push the times right on top of the plus. Next is the number 2. Off to the output it goes. We're at the end of the expression now. All that's left to do is empty out our operator tray onto the conveyor belt. And remember LIFO, last in, first out. So the times comes off first, followed by the plus. And there it is, our final postfix expression. 342 times plus. Okay, so let's just pause for a second. We just solved two problems that look totally different on the surface, but we used the exact same fundamental tool. Let's talk about why the stack is so darn effective for this. First off, the payoff is huge. Both of these solutions run in what we call O of n, or linear time. All that means is that they're incredibly efficient. We only have to look at each character in the string one time. Just a single pass, no going back, no rechecking. As the string gets longer, the work grows in a perfectly straight line. And in computer science, that's pretty much the gold standard. So why does it work so well? It's because at their heart, stacks are the perfect data structure for any problem that involves nesting or reversal. With the parentheses, it was all about tracking the nesting. With the math expression, it was about temporarily holding and reversing operators to respect precedence. And this isn't just some academic trick. This pattern is literally at the core of how programming languages are compiled, how web browsers parse code, and how databases understand your queries. It's powerful enough to even handle really tricky edge cases like unary minuses or right-to-left operators like exponents. The stack is just one of those fundamental tools you've got to have in your toolkit. We've seen it handle parentheses and operators, but now that you get the basic idea, here's a little something to think about. How would you tweak that shunting yard algorithm to also handle functions, something like max of a comma b? The core logic is exactly the same, and once you crack that, you've really unlocked a whole new level of parsing.